Sorry, wait a second. Okay. Hi, everyone. I'm Yuhao Li from Columbia University, and I'm very happy to be here in the Game and Equilibria workshop to present our work. This is a joint work with Chen and Mihalis Yannakakis, both from Columbia, and I'm going to talk about the query complexity of computing a fixed point in the contraction maps. So let me remind you what is a contraction. We say a function to be a 1 minus gamma contraction, where gamma is the contraction parameter. If you take any 2 points, the distance between these the image of these 2 points is strictly smaller than the previous distance. So like this picture, if you take 2 points, they should map to a closer pair of points. And we specifically require here's a Lipschitz constant, which is 1 minus gamma, to make it not extremely close to 1.
Can you remind us what is this distance metric?
Oh, right. Sorry. So yeah, we are working on this infinite norm, where
which means
the distance is just defined as the maximal coordinate of where the coordinate where
the Hamming distance.
Yeah, the Hamming. Yeah.
It's the Hamming distance, right?
It's the maximum norm. Like the coordinate where there.
The number of coordinates you need to change.
No. It's this is a continuous cube. Like it's a 0, 1.
Oh, this is a continuous thing.
Yeah.
Okay, I'm sorry. I'm living in a binary world.
Oh, right. Sorry, it's confusing.
This is between the interval 0 to 1. Okay, okay, that's very different.
So it's just an infinite norm.
Yeah. Okay.
Yeah, the norm is kind of important. Like as we will see in the end of this talk, like this norm may matter. Like if you consider the complexity of computing such a fixed point. So the famous theorem by Banach is that every contraction map has a unique fixed point. So a fixed point just means a point x such that fx equals x. Banach fixed point in general has many applications in both mathematics and computer science. For example, it can be used to prove some theorem in mathematics, and in computer science, it has applications for Markov decision process and many classic dynamic programming problems. I guess the most relevant part is that it subsumes the stochastic mean payoff and parity games. So we are interested in the complexity of computing such a fixed point. Here we are in the query model, where we have a query access to the function f, which just means I give you a point x, the oracle will tell you what is fx. And then we want to find an epsilon approximate fixed point by as few queries as possible. Here, the epsilon approximate just means the point x such that fx minus x still in the infinite norm is at most epsilon. So 2 remarks on the approximation. The first one is saying like is the necessity, which is the exact, because we are working on a black box model. So the underlying function has a unique fixed point, but the unique fixed point may be irrational. So it may be not feasible to compute the exact fixed point. So this is the necessity to study the epsilon approximate fixed point. And the sufficiency is that in most cases that we care about the applications, epsilon approximate fixed point suffices. The best algorithm state of the art is like log 1 over epsilon to the k almost 20 years ago. And the goal of this problem is to have a algorithm with polynomial in k log 1 over epsilon and log 1 over gamma. So this k is that dimension. Gamma is the contraction parameter. Like this is gamma, epsilon is the approximation, and k is the dimension. Yeah.
So you want to improve from log to the power k to polylog of k.
No. So polynomial, like this is an exponential in k, for example, but it's worse than that. But so eventually the goal is to have this complexity. So if we have such a polynomial, like polynomial in this sense algorithm, then we can claim, for example, simple stochastic image in P. And we will see it later.
Suppose you meet the goal, what would it mean for parity games?
This also implies parity game is in P, because parity game in P, yes.
Okay, go for it.
So yeah, so here we come to the motivation about all these games. So we know there's a chain of reduction where parity game is the easiest one, and the middle one is mean payoff game and simple stochastic game. And simple stochastic game can be reduced to contraction fixed point. That's the motivation. And also, like this contraction fixed point, if you view it as a total search problem, it's a problem in TFNP. And I just want to briefly mention it is the contraction fixed point is below CLS, like it's a class that's intersection of PPAD and PLS, like two famous classes, but no completeness of contraction is known and no lower bound. So it is really possible that this contraction fixed point can be solved in polynomial time. I guess the most important part for fixed point theorem is their existence, right? Like there always exists a fixed point. So in this case, for the contraction, it's actually very easy to show existence, and it's a constructive proof. So let's say we start from any point x0 in the cube, like k-dimensional 0, 1 cube, and we follow the path where we define x1 to be fx0, x2 to be fx1, and so we get a sequence of paths. So then it's easy to show that the distance of like the xn plus 1 and xn is at most 1 minus gamma to the n. So the claim is that this sequence, like start from any point, the sequence converges to a fixed point. And in fact, if you take the number of steps n to be roughly log 1 over gamma times log 1 over epsilon, then we can find such a fixed point, like epsilon approximate fixed point as we want. But this is not a polynomial algorithm, as we said, because it's the polynomial should have dependence on log 1 over gamma. So this naive path following algorithm is not sufficient to have any better like algorithm claim for games. Now we get to the like reduction, the motivation. Like I will show you that a simple stochastic game is reduced to the contraction fixed point to motivate why this parameter needs to be logarithmic, and also refresh our memory about the games. I guess we all know what a simple stochastic game is. A game on graph. We have three types of nodes: max nodes, mean node, and random nodes. And we also have two special sinks. One is called zero sink, the other is called one sink. And we have a pebble on the node. If the pebble is on the max node, the max player can control the next move. And if it is on the mean node, then the mean player can control its next move. If it's on the random node, then it will go to like either successor with half probability. So the objective is for both like max or mean player is to maximize or minimize the probability of getting to the one sink. The complexity of simple stochastic game is a long-standing open problem. Currently, we only know, let's say, it's in the intersection of NP and co-NP, and that's just because the one-player version of this game can be solved in polynomial time. Where by one player, it just means, let's say, the graph only has mean player and random nodes, but no node is controlled by the max player. And in fact, we have a better complexity upper bound for simple stochastic game, which is UP intersect co-UP. Here, UP stands for NP, but we have a further promise that the certificate is guaranteed to be unique. It's promised to be unique. So to show a problem in UP, you have to have a non-deterministic Turing machine where you have only one branch to accept the string. So to show this upper bound, like we will consider to reduce this simple stochastic scheme to a system of max, mean, and linear equations. In particular, suppose we have a node I, and it has two subsequent nodes j and k. So we will assign a variable vi to this node I, and we define it to be like the system equations is going to be, if I is controlled by the max player, then it's defined by the max of Vg and Vk, where Vg and Vk are variables corresponding to these nodes. And similarly, if it's mean, then it's defined as mean of these two variables. If it's a random variable, then it's 1/2 of Vg plus Vk. And we also require like this 0 sinc and 1 sinc to be 0 and 1 respectively. So let's say this system of equations is defined by V equals FV. So this is exactly a fixed point. Oh, F is this system of equations. So F. So let's say V is a vector. V is this value vector, and F Vi is this max or mean or linear equations. It's easy to see that this function. Sorry. Oh yeah, I'm going to talk about this. This is a non-expansive map, which means if we consider the Lipschitz constant here, it's only 1. It's not strictly less than 1. So by now we cannot apply the Banach fixed point theorem because it's not a contraction, but we can just times like contraction parameter 1 minus gamma to define a new function to make it contraction. And then by Banach fixed point theorem, we know there's a unique fixed point. So we can use this unique. You can also think about this reduction as reducing simple stochastic game to the non-stopping game. So by Banach fixed point theorem, we have a unique fixed point, and we are going to use this unique fixed point as the unique certificate to show this UP intersect co-UP upper bound. And in this case, if the underlying function is generated by simple stochastic game, we can guarantee that the unique fixed point is rational, and it has polybit description, which means it can be used as a polyset certificate. 2 remarks of the reduction.
So, how did you make it a contraction?
Oh, like we will artificially times a contraction parameter that's going to be extremely close to 1. So that we will not.
How does it matter? What is the significance of the closeness to 1?
Oh, it's only because of that we can make sure that we will not lose too much information to solve this simple stochastic game. Think about this gamma to be like n is the number of vertices. Gamma is going to be inverse exponential in n.
I see. Okay.
So that's exactly why that in this reduction, both epsilon, like this approximation parameter, and gamma needs to be inverse exponential. So that's why when we try to find a fixed point of contraction maps, the dependence of like the complexity dependence needs to be polynomial in n, which is the number of vertices, and logarithmic of epsilon and logarithmic of gamma. So that's how we make it to be polynomial time. Yeah, and in fact, if we don't care about this UP intersect co-UP upper bound for simple stochastic game, yeah, we can just find like even not exact fixed point, like even epsilon approximate fixed point suffice, but that has to have very good precision, approximation precision. Okay, so I'm at if I'm wrong, please correct me, but this reduction, like through contraction maps, is the only way that I know how to show simple stochastic game is in UP intersect co-UP. I don't know any other.
So what is the meaning of epsilon approximation?
Oh.
Can you say what is the meaning of that epsilon approximations are sufficient?
Yeah, I mean, so previously we were trying to find the exact unique fixed point, but I'm saying here, like in this reduction, even if so, this is the function defined by a simple stochastic game, and this is the artificial function that we times the 1 minus gamma. Even if we can find the epsilon, not exact epsilon approximate fixed point of this function, that can help us to solve simple stochastic game. But the epsilon parameter has to be very, very close to 0. Basically, yeah.
Because of the polybit description.
Yes, yes, yes. Okay, so this is the motivation, and we have specified that in this in this reduction, this epsilon and gamma is roughly inverse exponential. And what's best known for this game is simple stochastic game is exponential time mean pair of game. We have pseudo polynomial which in worst case is also exponential. Paired game, we have quasi-polytime algorithm. So you may ask why we study the query.
Go back to that slide.
Yeah.
Let's suppose you start from parity game.
Sorry,
Okay.
what?
What will you still need 1/2 to the poly in the number of nodes in the arena?
Yes. To solve the parity, even for parity game.
Even
that
for
needs
parity
to be-
game, you need this level of precision.
Yes. Okay. Yeah. Otherwise, the problem can be solved very easy. Like if gamma is a inverse polynomial, you can just value iteration to solve it.
Well, one can hope. Yeah.
Yeah, one can hope. Yeah. But at least this reduction has to have this precision. So you may ask why we study this query model, because like it's reasonable to ask because we have such explicit functions, just the max, mean, and linear equations. But the problem is that we just don't know how to work on them, even if it's explicit, beyond evaluating the function values. This is usually the case of in the study of fixed point computation, where even if we are given an explicit function of the underlying fixed point problem, we don't really know how to use it beyond like evaluating the function values. And there's probably a more well understood example, which is called Brouwer fixed point. So maybe let's take a short detour to the Brouwer, and I will show you, like in this case, even for explicit function, we cannot hope to solve it. So Brouwer is we all know it's a fixed point. It's complete for this class PPAD, and it's closely related to contraction, where we have exactly the same problem statement. But now the Lipschitz constant is no longer strictly smaller than 1, but it's just some parameter L, where L could be any constant, like from 0 to infinity. And the Brouwer fixed point theorem is a more general theorem than Banach. It says every continuous function has a unique fixed point. Every continuous function has a fixed point. And we can extend it to this 0, 1 to the k. That's very easy. But the point is, Brouwer can only guarantee existence of fixed point, but not unique fixed point. So that's the significance of contraction. This is a diagram where when L is smaller than 1, this is contraction, and we have a unique fixed point. When L is larger than 1, this is guaranteed by Brouwer, but we could have multiple fixed points. And when L is exactly 1, this is so-called non-expansion. We could still have multiple fixed points. For example, consider the identical function. Like every point is a fixed point, and it's a non-expansion function. So the complexity of Brouwer is well understood. For example, we have exponential query lower bound. We also know it is PPAD complete, where PPAD is a class that's believed to be not equal to P. And you may ask, like, let's say we want to find a fixed point of Brouwer, but we only want to consider explicit functions. Like we don't want to consider general Brouwer. That's not interesting. Then I guess the most interesting case is to compute a Nash equilibrium, where Nash equilibrium, if you consider the Brouwer function, is such a kind of explicit function. I give you, let's say, two matrices. You can define this kind of function by plus and like max of 0 minus and deviation. Is a relatively explicit function. So the celebrated theorems tells us that computing a Nash equilibrium even in two-player game is PPAD complete. So this can be interpreted as computing a Nash equilibrium is as hard as computing a general Brouwer fixed point. So this just means even if you just want to solve Nash equilibrium as an explicit function, it's really the same as arbitrary explicit Brouwer fixed point. Yeah, so back to contraction. Of course, we are interested in what is the complexity of contraction. We don't really understand it. And now I'm going to tell you about our results. So remember, we are working on this query model where we have query access, and we want to find epsilon approximate fixed point as few using as few queries as possible, and we want efficient which means polynomial in k log 1 over epsilon log 1 over gamma. And our main theorem is that we give a polynomial query algorithm for contraction fixed points. Here, the polynomial is really a small polynomial. It's a k squared times log 1 over epsilon. Yes, I will get there later. However, this algorithm is not time efficient. So I'm not claiming that it's not time efficient. So I'm not claiming that simple stochastic game is in P, but it is query efficient. Just to illustrate the results, so when
why is it not efficient? Because the query, you have the actual function, right? You can
Yes.
compute it fairly easily.
Exactly, but our algorithm used the fact that to determine the next query point, we may need a brute force procedure. So that's where our algorithm is not time efficient, and I will get there. Yeah. So this is a small diagram where we know now that for contraction, it actually has polynomial query complexity. But for like, I don't know, L to be 1.001, the Brouwer fixed point, it has exponential query lower bound. And let's not bother us for the case where L equals 1, and I will get it later. Yeah. Sorry. So
what happens when L is equal to 1?
Yeah, I will get there later. Yeah. Thanks for the question. So one sentence of this result is that it makes contraction in a very intriguing complex status, and I will explain it later. So I will use a couple of slides to introduce the techniques, and now and you are going to see why it is not time efficient. So let's say this is a two-dimensional contraction problem. This is just 0, 1 to the 0, 1 square. And let's say the first query point is, of course, the center point. So we query it. Then we partition the square into 4 regions, where the regions defined as, if you look at the point, the distance of this point and the query point is defined by which coordinate. Remember, we are working on the infinite norm, so the distance is always defined by some coordinate. In this case, for example, this part is defined by the first coordinate. This part is also defined by the first coordinate, but they are like minus and plus the signs. And these 2 regions are defined by the second coordinate. And for higher dimension, we can also define such a thing. It's going to be strange, but for query point, you can still define, like for the first coordinate, this is the region, and this is the minus part region, and this is the plus part region. You can always do that. Now for the 2-dimensional case, let's say we query this point, and we will analyze the information by coordinate. Let's say this point, for the first coordinate, it moves right, and for the second coordinate, it moves up. Then I'm claiming that every point in this blue region has to go up, and every point in this green region has to go right. This means all these points cannot be fixed points because they moved. And the reason is just by contraction condition, where remember the distance between any point in this green region and this point is defined by the first coordinate. And this point moves along the first coordinate a little bit. So because the distance should like be contracting or at least non-expansion. So all these points should have this kind of movement along the first coordinate. And you can do the same thing for the 3D. Oh, by the way, this tells us we make good progress where we only use one query to shave the search space by half. So this is a very, very good progress. And we can still do that for higher dimension. Like for example, for 3D, if this point goes right for the first coordinate, then we can remove all this blue points. So that's true. But the point is, for higher dimension, after removing these regions, the remaining region will be not convex. So if you look at this picture, the remaining shape is kind of nice. It's convex or whatever. But for higher dimension, like when k is 3 or larger, then this is not going to be true. So the challenge is that even for the first query, we can make a good progress. We don't know how to ensure this progress for future queries. And so one technical part that we need to show is that there always exists a next point we need to query. And let's call it a center or balanced point in our paper. So the balanced point means it's a combinatorial definition where, let's say we have a grid and we consider the discrete grid. And suppose you can pick arbitrary subset of the points. Let's say this blue points, arbitrary subset. What I can show is that there exists a grid point such that if you do the partition as usual, there exists one coordinate where both sides contains a large fraction of the points, a large fraction of the blue points. In particular, 1/2k, where k is the dimension. So this means we can basically just query this point, and whatever the answer we get, we can eliminate a large fraction of the candidate points. This blue points are viewed as a candidate points. So the progress is not as good as before. It's not 1/2, but now it's like 1/2k. So that's why our eventual algorithm has query complexity k squared times log 1 over epsilon. So it's instead of k times log 1 over epsilon. But that's why. And the reason that our algorithm is not time efficient is really because we can only show the existence of such a green point, this balanced point, but we don't have a good procedure to find it. So this is a query algorithm where the first query is trivial. Even for the second query, where to query it is no longer trivial. We have to have we know such a point exists, so we have to have a brute force procedure to find such a point and query it. So that's query efficient, but not time efficient. So now we get there. How about L equals 1? The answer is actually that it depends. So if we consider the original definition where we want to find a point x such that fx minus x is at most epsilon, this is so-called weak approximation, then our algorithm actually shows that even for L equals 1, we have polynomial query complexity. Despite it may have multiple fixed points. So we don't have a uniqueness guarantee, but we can show it has a polynomial query complexity. But if we want to find a kind of strong approximation fixed point, which just means we want to find a point that is geometrically close to a real fixed point, then what we can show is that when L equals 1, it has infinite, it needs infinite many queries. But for when L is strictly smaller than 1, we still have polynomial query complexity. So this is what's happening about L equals 1. So in general, the fixed point computation is such a small field where we want to, given some interesting fixed point problem, we want to compute such a fixed point. And for many famous fixed point theorem, we have a very good understanding. For example, this Borsuk-Ulam, which is complete for PPA, this Brouwer, which is complete for PPAD. But we also have these two fixed points, contraction and Tarski. We only know, KKT is a optimization notion where you want to find basically a solution of gradient descent. So KKT is complete for the intersection of PPAD and PLS, which is CLS. But we also have these two fixed points that probably we care most in this community because simple stochastic game can be reduced to both of them. Like they subsume both of them subsume simple stochastic game and all these parity games, min-PELF games. We only know they are below CLS and we don't know any lower bound. They have kind of interesting status where we know it is in CLS and we don't know how to prove a query lower bound for these two fixed point problems. And probably you have heard Tarski like a few years ago from Kusha's talk that was about the Tarski fixed point. And currently we still don't have an improved query lower bound since his talk. But But now contraction is a bit more interesting because we can show query lower bound is just impossible because we have polynomial query upper bound. And what does it mean? But it's not a time-efficient algorithm, so what does it mean? Here we have such an interpretation where for all other fixed point problems, whenever we can show it's complete for some TFNP classes, they have exponential query lower bound. And in fact, if you want to prove a fixed point problem that is complete for some class, the first thing that we did is to prove a query lower bound, exponential query lower bound. However, this story for contraction fixed point is totally different because that's just not possible. We have query upper bound. So if one believes that the problem, for example, simple stochastic game is actually hard, it's not in P, then this will imply that contraction fixed point is also hard, it's not in P. But then we need to brainstorm how to show hardness about it because we cannot rely on query complexity. And it will need to go beyond traditional wisdom about how to show hardness in TFNP. We are a little bit more optimistic, and we hope that this query algorithm may help design time-efficient algorithms for contraction and simple stochastic games, ultimately maybe polynomial time algorithms. And a few open problems. The first is, of course, the time complexity. And also, it's also interesting to study the contraction fixed point about other P norm. As I said, we were working on this infinite norm, and the only known result is that for other norm is that we have a polynomial query and a polynomial time algorithm for norm to norm. But beyond this, we don't know anything about other P norm. And that's it. Thank you.
So when people solve, I think, MDP, you could just reduce it to linear equations, but they're very large.
Yes.
People actually use value iteration. So they actually end up using, there is a polynomial algorithm, but instead they're using contraction mapping. Value iteration is essentially contraction mapping. Mm-hmm. It doesn't have such nice bound. It seems to work better in practice. Mm-hmm. So what's going on here?
I guess it's the dependence of gamma, like the contraction parameter. Oh, you mean in practice or in theory?
I mean, that's how people usually solve large MDPs, value iteration. Essentially is applying, it's not the query model, of course, they apply the function explicitly.
Yes,
okay?
Yes. Yeah, but we all know that value iteration in practice has a very good performance, not necessarily for games, but also linear programming and whatever. Like, yeah. But we also know that in theory we can just prove exponential lower bound of any value iteration algorithms. So I guess this is so we know a complete answer in theory. So I guess this is more like a question that's the theory and practice gap, which probably can be answered by smooth analysis and other things. I don't know. Yeah.
Just a clarification. So in your balanced point slide, what are the blue points? Why are they the candidates?
Oh, I see. So the setup is, suppose we have queried a few points. Then we have eliminated some set of the points. Then the remaining point will be the so-called candidate points. Like we know some point cannot be fixed point, and some point might be fixed point. That's called candidate points. And we don't have any structure guarantee of that point. It's just arbitrary subset of these grid points. Now we want to show that there always exists a so-called balanced point, where as long as you query it, you can eliminate the candidate points, like a large fraction of it. So probably this lemma is a little bit overkill because we do have some structure of the candidate points, but the shape is weird. We don't know how to work on it.
I have a question about exactly the same slide. So, okay, there is like guessing, but can you do probabilistically? Like you say that you eliminate some trivial points, and then from the rest, like randomly taking one point, the random walk over these guesses would be kind of short, and you get a probabilistic algorithm that's
Yeah.
approximating faster.
Yeah, I would say any better algorithm is possible. Like we didn't really do a hard work on like optimizing this algorithm for finding balanced point. But there do exist. Sorry, there do have some very nice structure where you can hope on a better algorithm for that. Probabilistic algorithm is one choice. Yeah.
Have you identified any interesting special cases of contraction for which you can do better than brute force?
You mean when searching this balance point? No, we didn't. Right. Yeah. For example, we could try to see if the function generated by simple stochastic game, if it has better structure, and probably we can do better than brute force. But it's not trivial. It's not obvious.
So what you said about your technique seems like it relies very heavily on using L infinity norm. So what was the result for L2 that you mentioned at the end?
Yeah. Very good question. So for L2, it's actually a much easier algorithm where L2 has a very nice geometry structure, and you can just use ellipsoid method to solve it. So that's a polyquery and polytime algorithm.
Any other question? Okay, then thank you. Thank you, Yuhao.